Welcome to qnawire.
In this question, you have a ball that is dropped from a height of 1.75 meters and it bounces off the floor and then comes back up to a height of 1.5 meters. And you want to calculate the force or the impulse that the floor exerts on the ball, and then you want to estimate the size of the force that the floor exerts on the ball. So for impulse, you know that the impulse, which is just the force times the time, is equal to the change in momentum. So we know, so there's two separate incidences that you want to consider here. So you want to consider the first part, which is this thing falling to the ground and then the floor stopping it all the way to zero, and then the floor exerting another force to accelerate this thing back up to a certain speed so that it reaches 1.5. So this will make the situation slightly easier to calculate. So in this case, I'm going to choose energy conservation laws to calculate the speed that this thing travels at. So you know that if it's coming from a certain height um, and it reaches the floor, by the time it reaches the floor, it has maximum kinetic energy, but all the potential energy is now being converted to kinetic energy. So the potential energy is zero. So there's an exchange of energy that happens here. So essentially what we can do is we can just say the kinetic energy or the potential energy that this mass has is now equal to the kinetic energy that this ball has by the time it strikes the floor. So this says that all the energy, all the potential energy was converted into kinetic energy right before this thing hits the floor. So the mass is common. So what you find is that the velocity is just equal to 2gh, just the square root of that whole quantity. So if we do this for this falling part, we can also do the same thing here, where this thing has kinetic energy at the bottom, and it's going to lose that kinetic energy or convert it to potential energy by the time it gets to this height. So we can use the same equation to calculate the velocity that this thing has going up as well. So if you do this for the falling motion, you find that that velocity is around 5.86 or something like that meters per second. And then if you use the same equations for the return motion, you find that that velocity is going to be equal to now 2 times the gravitational constant times the height that you get, and then you can get that velocity as well. So that's going to be, so in this case, you have 2 times 9.8 multiplied by 1.5, and then you take the square root of that. So that'll give you something around 5.4 for this part of the motion. So over here, this thing had, this V is 5.4 meters per second. So you now have the two velocities over here. So you just want to calculate the change in momentum. So because you want to use that equation here. So you can do it again in two segments. You can calculate the change in momentum here and change in momentum here, and then add them together to find the total change in momentum. Or you can just do, so this thing is traveling at 5.86 here, and then it's going to have a negative velocity going the other way with 5.4. So if you combine those velocities, multiply them by the mass, what you find is that the total change in momentum for the system is around 3.83. Now remember, so since this is a change in momentum, or this is just a force times time. This is just Newton seconds, essentially. Or you can have other units as well that have mass and the velocity and the time as well, if you want. So this comes from the change in momentum over here is around 1.776. The change in momentum here is about 1.62, which would give you 3.83. And then the next part is asking you to calculate the average size of the force that would be exerted on the system for this to happen. So if you know, if let's say we estimate that the time of contact between the ball and the floor is around 1/4 of a second. So once you know this, you know that the force is just going to be the impulse over time. So we can just say the force in this case will be just the impulse over the time, which will give us 3.83 divided by 0.25, which would be around 13.5 newtons or so. So this answer just depends on what you estimate for the time of this collision over here.